Welcome to the AI Research Roundup. I'm Alex. Alright, today we're diving into a paper published on April 24th, 2025, titled RAGEN, Understanding Self-Evolution in LLM Agents via Multi-Turn Reinforcement Learning. This research tackles the tricky problem of training LLMs to act as interactive agents, especially when they need to make many decisions in a row and deal with unpredictable or stochastic environments where outcomes aren't always certain. The authors introduce a new framework called StarPO and a system called RAGEN to improve how these agents learn through multi-turn interactions, finding that without very specific reward signals, true reasoning is hard to achieve. And for those looking to dive into the practical side, the authors also shared their GitHub repo for RAGEN. It's where you'll find the code to implement their reinforcement learning approach for these LLM agents. Looks like it has, well, setup scripts, config files, the main training scripts, and even some documentation to get you going. That GitHub repo, it's all about implementing their new framework. They call it StarPO, which stands for State Thinking Actions Reward Policy Optimization. This State Thinking Actions Reward Policy Optimization is their approach for what's called trajectory level reinforcement learning. This means the LLM agent learns from a whole sequence of interactions, not just one-off decisions. And at each step, it even tries to, think out its reasoning before giving an answer. Such an approach is really key for agents needing many decisions in a row, especially in unpredictable environments. And the RAGEN system is the practical setup they built to train these agents using the State Thinking Actions Reward Policy Optimization framework. Alright, so to test how agents learn with the State Thinking Actions Reward Policy Optimization framework, they use several environments. This figure shows 1, the Biarm Bandit. Here, the agent chooses between a low-risk Phoenix arm and a high-risk Dragon arm. Initially, at step 20, it prefers low risk. But later, at step 60, it reasons that the high-risk Dragon arm might yield better returns. Its reward is stochastic, meaning uncertain, and it's described by a Bernoulli distribution, which is a probability model for a simple yes-no outcome, like getting a reward or not. This setup helps assess risk management learning. Okay, so moving on from the Biarm Bandit, this figure shows 2 other environments used for testing. On the left, we have Sokoban. This is a multi-turn puzzle, but unlike the Bandit, it's deterministic, meaning actions have predictable outcomes. The agent's job is to push boxes onto target locations, and crucially, these moves are irreversible, so it needs careful planning. Then on the right, there's Frozen Lake. This one is also multi-turn, but it reintroduces stochasticity, similar to the Bandit. Here, the agent might randomly slip when trying to move, requiring it to adapt to that uncertainty to reach a gift. For both, the figure shows the text-based view the agent sees and a visual representation. The problem in these environments is often framed as a Markov decision process, or MDP. A Markov decision process is a mathematical framework for modeling decision-making in situations where outcomes are partly random and partly under the control of a decision-maker, like our LLM agent. Okay, so we've discussed those environments like Sokoban and Frozen Lake and how they're modeled as a Markov decision process. This figure now shows us the average success rate of the agents when trained using their State Thinking Actions Reward Policy Optimization framework, specifically looking at 2 variants. One is called Proximal Policy Optimization, or PPO, which is a reinforcement learning algorithm that aims to make an agent's learning process more stable by limiting how much its decision-making strategy can change in each update. It often uses what's called a critic, which is like an internal judge, to estimate how good its actions are. The other variant, GRPO, is shown in blue. What's striking here is that while both initially improve, performance often collapses later, especially in those multi-turn tasks. You can see proximal policy optimization, in orange, generally holds up better than GRPO, particularly in Bandit and Sokoban, suggesting that using a critic helps resist this performance drop when dealing with long sequences of decisions. Alright, so we saw how the baseline State Thinking Actions Reward Policy Optimization framework, especially when using proximal policy optimization, could still suffer from performance collapse. Well, this figure now introduces an improved version called StarPOS, shown in orange, and compares it to the vanilla StarPO with proximal policy optimization, which is the blue line we saw struggle before. Across all three tasks, Bandit, Sukoban, and Frozen Lake, you can see that StarPOS achieves a higher success rate, and crucially, it either completely avoids or significantly delays that performance collapse we were just talking about. This suggests that the modifications in StarPOS are really effective at stabilizing the learning process. It's clear that StarPOS really makes a difference in these multi-turn scenarios. Overall, this research into RAGEN highlights how LLM agents can indeed self-evolve through reinforcement learning, but also points to the critical need for stable learning algorithms like StarPOS to prevent performance collapse. Understanding this dynamic is crucial as we build more capable and autonomous AI agents. Thanks for tuning in to the AI Research Roundup. I'm Alex, and I'll catch you next time.